Does everybody see the actual Python decal? Yeah. Okay. Cool. So in that case, let's go ahead and get started today. Or it's week 5, Monday, February 22nd, I believe. Today we're going to be talking about a couple things, but first we have some announcements. Remember, your homework 3 is due on Wednesday. Make sure you get that done. There's office hours today, tomorrow, Wednesday, and there's always one on Friday as well. So make sure you come to any one of our office hours to get the help that you need. We always want to make sure that you're getting the help you deserve. Office hours, thanks for those of you who showed up, and make sure you come to them. And then attendance, there's a link right here. I'll put it in the chat one more time. And just for those watching, but also, it was there for those that are watching asynchronously. So let's go ahead and recap from last week on Wednesday. So we're going to do some breakout rooms. The questions for our breakout rooms are: what is the difference between a NumPy array and a Python list? And then why would you ever want to use a 2D array? Like, what do they remind you of? What are they kind of used for? So we're going to talk about that in breakout rooms. We're only going to do 2 breakout rooms, I think. There's only like 9 of us here. So yeah, so just remember these, and then I'm going to set up the breakout rooms. We'll discuss for maybe 5 minutes, maybe 3 or something like that. All right, we'll open all the rooms. I'll see you guys in a couple minutes. Okay, so would anybody like to share at least their answer to the first question or the second question? Doesn't really matter. I'd really appreciate somebody to volunteer to answer.
Yeah, I can answer the first question.
Okay, cool.
So I just remember with a list, you couldn't do operations between individual components between 2 lists. If you added something, it would just add it onto the end of the list. But with NumPy array, you can do operations between each component on one list with the corresponding component on the other list. So you can add them like vectors or like matrices.
Yeah, definitely. Thank you. Also, just to add on top of that, NumPy array comes from a different library. It has a different set of rules that I think are a bit more intuitive in a lot of ways. Some are not, but most of them are a lot more intuitive. But yeah, it's a lot more useful for doing things like manipulation to large amounts of numbers. And then would anybody like to share with what they said for the second point?
Yeah, I can share. So they remind me of matrices, I guess, and you might want to use it if you're processing data for a research project or something, and you want to have a big, because that wouldn't be good for a list. It would be better for an array.
Mm-hmm. Yeah, and also my favorite example is if you wanted to take a picture, say you took a photo on your phone and you wanted to manipulate the actual pixels. Well, that's a grid of however many pixels by however many pixels your camera can store, and how good your camera is, and you can actually index pixel by pixel on that picture if you think of it as a 2D array matrix where 0 0 is the very far left, and then however many XX is the top right or whatever. So that's pretty cool. And then same thing, and that logic can be applied to telescope CCD pictures, just like a phone camera. It's just a different object. So if you wanted to maybe average over all of the different pixels of a galaxy that you took a picture of, and you want to figure out its mean brightness or something, or mean flux on your camera, then by all means you can just you run a little Python script and you can calculate what that might be for that galaxy, which is pretty cool. Pretty cool stuff, applications for photometry. Thank you for everybody who shared. So I want to talk a little bit about, I want to patch up a little bit of holes that we didn't cover last week about NumPy, and then we're going to talk a little bit about file manipulation, or not file manipulation, but file I/O, downloading some data, opening data, closing data onto your notebook, and how you can work with it. And then we're going to get into how to plot. We're going to start plotting this week. And that's probably the most important topic for an astronomer. Plots are super important in astronomy and science. But you'll see plots everywhere. They're in every paper. I'm almost certain of it. They're in textbooks. They're everywhere in your upper divs. They're going to make you plot lots of different models and stuff on your homework assignments. And it's just super, super useful to know how to plot and know how to plot well. So we're going to talk about that. But first, a little bit of extra stuff on NumPy. So let's say you wanted to create like a specific range of numbers or items. We talked about it a little bit with the built-in range function in Python, and that just lets you literally make a list per se. It's not actually a list; it's called iterable, but it doesn't matter. It's the same thing as a list for all our purposes. And it's just a list of numbers that goes from whatever you say to start at to whatever you end at, going by integer steps. So if I put like 1, 10, it's going to go from 1 to 10, not including the very last digit 10. It goes from like 1 to 9 technically, and it makes that list, and you can iterate over that list of just pure integer numbers. And then like that is a good way of keeping track of how many steps you want to do. But NumPy has its own version of that. It's called arange. It's a little bit more robust, I guess you could say. They do the exact same thing though, and I think I just like using NumPy when I do any of my stuff. I keep everything in NumPy in general. It's just kind of easier to remember all their syntax than anything else. So numpy.arange is the same thing as range in Python, with a slightly different syntax, I guess you'd say. So you say your starting index, you say your stopping index, and then the number of like the step increments you want to do. So if you want to go from 1 to 10, but you want to skip every other number, you put 2 for your step. If you wanted to just go 1 by 1, 1, 1, or like increment by 1 integer at a time, then you do step size 1, and so on. However many you want to skip by is the number for your step, which is super useful if you want to, have like integer numbers or non-integer numbers. I'm pretty sure you can also apply that to like decimals. If you wanted to start at 0.5 and end at 0.5, you can step by 1 there, and it would give you every half number, or it would go by like 1/2, 3/2, so on. So that's super useful. Then there's numpy.linspace. This is the most important for plotting. You're almost always going to use a linspace or a log space. They're like the same thing, just one's in linear scale, one's in log space scale. But linspace creates an array from a start to a stop, evenly spaced by a number of steps. So let's say I want to calculate, or I want to get an array, an array of numbers from 0 to 2 pi, because I want to plot cosine. I want to know exactly how cosine changes. So I'm going to make a giant array, say 1,000 steps, which means that the dx, or that little like incremental dx, or like dx in between every entry in your linspace array is going to be really, really small. It's going to be it's going to be like whatever the range is divided by 1,000. So if it's from 0 to 2 pi, it's going to be 2 pi over 1,000. That's your little dx. That's what that number of steps means, and then that will actually plot 1,000 points between 0 to 2 pi. And the higher those points are, the smoother your plot will be. But if you make it really, really high, it's obviously going to be a lot more numbers to deal with, so your computer slows down. So usually if you're doing like a continuous function, you usually pick between like maybe 100 or like 1,000 points, something like that. Usually I do like 100 or 200 points just to start, and then if I need more resolution, then I increase the number of the steps, like the number of steps. But yeah, numpy.linspace is super important for plotting. Cool. So let's move on to how do we get data. Before I move on, actually, does anybody have any questions about like the linspace or array? Or arange, I mean. Okay, I don't think so. So in that case, we'll just move on. Hope you guys like my meme. I worked hard on it. We're going to talk about file IO. File IO, whenever somebody says that, just means like opening a data file in your notebook and closing a data file, or like writing to that data file. So if you want to load some values, say a text file, into your notebook, how do you do that? Like, let's say I download a huge data set of COVID data or something. Hint, that's going to be one of your homework assignments. But let's say I have like this giant text file that has like thousands and thousands of numbers. How do I put that information into my notebook so I can work with it? Say, plot the average case toll, or like cases by day or by month or whatever, however the data is formatted, or, like find a trend, make a histogram, you name it. How do I go about doing that? Well, first you need to load that file in. And how do you do that? You use something called numpy.loadText. There's other ways of doing this, and we'll talk about that a little bit more later. But I think the best way to start to learn how to do it is with NumPy. So I love NumPy. So np.loadText or numpy.loadText, it's the special function that you use to load in a text file. It should be on your third homework assignment, and it kind of walks in a lot more depth. So I'm not going to talk about it so much here. I'm just going to kind of point out what it is and how, like, what it's meant to do. So numpy.loadText, you always start with your file name. So that should be in the same directory as your notebook. So you'll notice on your homework assignment this week, I put the homework notebook along with like a data file next to it. They should be together. You should keep those together. They should be in the same folder or same directory. So that way you can just immediately do the file name. Now, if your file's in a different directory, you're going to have to include your different like commands in the directory tree. So in the case of, let's say it's like in a folder inside of the like folder that you're already in, then you would need to do like backslash the folder name, or backslash the folder backslash the name of the file. But for ease, just keep the data file in the same directory as your notebook. That way you can just put the name of the file and it'll be able to find your data file. So usually these file types come in there's different file types. The one that I prefer to use the most is .csv file or .text file. I prefer CSV because it's really commonly used and it's kind of easy to work with. Microsoft Excel works with it really well. So I'm going to give you guys .csv files, but it'll work the same with the .text file, basically. What is delimiter? Delimiter is basically telling the software or the NumPy package, hey, I want you to look for whatever I specify this delimiter to be, and I want you to separate values by that. So if I set my delimiter equal to a comma, for example, I will go through the entire file, and every time I see a comma, I cut off that value that I just read. So for example, let's use a pointer. If I have like 69, comma 3, comma this number, comma 1, then what this will do, if I specify that the comma is the delimiter, it'll say 69. Oh, there's a comma, that's a number, and I'm going to put that as an entry in the list, or an array. Actually, it's going to go be an entry in the array, and then it's going to read after that comma, it's going to read the next bit of information. So hey, 3, and there's another comma. Oh, okay, 3 is another object in my array, and so on. And it'll go through your entire file like that. So delimiter tells the file what you're separating by. Skip rows, it's pretty self-explanatory. How many rows do you want to skip? Use calls, it tells you you're telling the function what columns you want to use. And then unpack equals false, unpack equals true. Which one do you pick? I'm going to let you explore that in your homework. I don't want to give that away, but if you have questions, come to office hours about it. It's just a way to format the data file into something that's workable or easy to work with. Sometimes you want to use it, sometimes you don't want to use it. So I'll let that be as an exercise on your homework. It walks you through what unpack should do. And by all means, I encourage you to Google things too and learn for yourself. But yeah, so that's a little bit about numpy.loadText. Is there any questions here?
So if you wanted to set your delimiter to like a comma, would it just be like quotes, comma?
I think so, yes.
Okay.
You can double check just by looking at the documentation too. It'll tell you exactly what delimiter types can be. So it might be like space, or it might be none, it might be comma. But yeah, it's usually a string that you set it to.
Do you have to write in all these things like the delimiter and the skip rows when you import a text file?
Not necessarily. Some of them are optional. Like use columns is an optional one. Skip rows is an optional one. File names, of course, mandatory. Delimiter, I'm pretty sure that's optional. And then unpack is, I believe, optional, but it might be required. I can't quite remember, but that's also specified. If you just Google numpy.loadText, it'll literally give you like the documentation, and it'll give you like all the nitty gritty details of what the function will do. So if you want, I can show a demo of that after, like at the end of lecture, just so you can see exactly what I mean when I tell you to look something up or like look up a function and its details. So I'll do that at the end. Is there any other questions?
Okay, thanks.
Okay, I'll take that as a no more questions. So let's move on to the next thing. Let me get rid of this laser pointer. Okay, so loading data from a text file. This is an example. Data is equal to np.loadText. This is my data file, sample data.text. Text file is very similar to a CSV file. The only difference is the text file is not separated by commas. So you don't need to, yeah, so this is an example. You don't actually need to put delimiter or unpack is equal to true. You don't need to put those, technically those are non-default, or those are already taken care of by default. But if you want to specify for more clarity for what you want to do, by all means you could do that. So I usually skip the header row. So sometimes you'll want to, like, a file will be formatted in such a way that the columns have text for like what they are. But if you already know what those are, then you don't need to worry about that. So usually skip that like header row, for example, or if there's multiple of them, then you skip multiple header rows. But yeah, anyway, you print the data and that'll give you a NumPy array with data in it. And then back to a little bit more stuff about NumPy with arrays. We can ask NumPy to find indexes of specific data using a function called numpy.where. So let's say you have an array of 10 numbers, but you only want to isolate numbers in your array that satisfy a condition. They don't have to be numbers; they can be anything, but numbers are the easiest to work with. So let's say I make a ranging or like an A range array from 0 to 10 or 0 to 10. And I want to take out every number in that array that's less than 5. How do I go about doing that? You use a function called numpy.where. So numpy.where, you put the condition in on the array that you're worried about. So let's say numpy.where a less than 5. That'll spit out a little funny formatted information at you, but this is kind of what it would look like. It gives you a tuple with the first index being, or the 0th index being the array that you want. That's like sorted through, and it's formatting the condition, so it takes out any number that doesn't satisfy that condition. And unless there's like a comma and then nothing after in the tuple, and it doesn't really make sense. So just know, just be aware if it's like giving you weird stuff, then just tack on like a bracket 0 to index into that 0th component of this tuple that it gives you. But don't worry about what that other stuff is. It's like there's like optional stuff that you can throw in there that gives you more information, but it's not important for our uses. This just might be useful on a homework assignment maybe. So just keep that in mind if you ever want to, use a condition to cut out a lot of your data and like isolate a certain amount of information in your arrays. This is how you do it. So, and then here's some examples. So again, with this A range, giving you a range of 10, it gives you this array from 0 to 9, always cutting off that last index. So then let's say I want to isolate all the numbers between 0 and 5, or like less than 5. And then after that, I want to take all the numbers that are remaining and I want to multiply them by 10. This is how you would do it. And it gives you back an array 0, 1, 2, 3, 4. And then starting at 5, since that's 5 and up, it'll multiply it by 10. And that's denoted by this syntax here. Cool. So that's just some examples. Any questions about that?
I'm kind of thinking back to the homework. Could you put in like a function instead of like 10, for example? Because wasn't there one homework problem where you had to do like the last part of a list was like even numbers or something?
So not entirely sure what you're referring to, but are you asking like how do you make like a list of only even numbers? Or an array of
I guess what I mean is like where you have 10 times a, could you put like a function there? Or like
I think so.
Okay.
I think so. Yeah. I mean, like, because all it's telling it to do is for every index in the list, do this to it. So if it's a function that takes an A and spits out, like a modified A, I think that should work. My intuition says that should work.
Okay, thanks.
Cool. Any other questions? Sweet. All right. So now let's get into the fun part. This is probably the most fun part about coding, is when you get to make really pretty plots that you can show to other scientists and friends and be like, yo, look at what I made. And these are kind of boring, but they'll get a lot cooler the more you learn about plots. And there's a lot of cool stuff you can do. So for example, you want to plot like a log plot of, I don't know, I believe this is like the core temperature of a star versus its age or something like that. This is something we had to do in Astro 160, if you ever want to take that class. I believe this is like, oh yes, this is denoting like sounds, or like it's called the Mach number, which is basically like the speed of a fluid relate like over the sound speed. And it's like really cool. You can make really cool contour plots that describe behavior kind of like in a 3D sense, you know, like a contour plot. For those of you that have taken 53, where you have X and Y, and then like Z is above the axis. These are like kind of contour plots, like you would think of like a geo map or something like that, or elevation map. This one's like, you can do water vapor, you can put dashed lines and so on, yada, yada, yada. Lots of different examples, but this is like how we analyze it. This is how we do it visually. This, you could put a ton of information into a picture. A picture contains 1,000 words at least, right? Or there's like some metaphor or something like that. So very, very powerful tool. So what package do you use to plot? How do you do that? Use a package called import, or it's not called import. You import matplotlib.pyplot as plot. This is like the standard syntax for plotting. So you put this at the top of your data file. I mean, not your data file, the top of your notebook. So along with your import numpy as np or something, import random, import math, whatever, you put import matplotlib.pyplot as plot. And what this does is it gives you the whole library on how to plot, all the tools that come with it. So let's talk about how you use it. Yeah, this look, it's pretty pretty. So let's start with the simplest plot we can do, and we'll move our way up for more complicated plots. So the simplest plot is probably a line. So how do you do it? We're going to use PLT. That's the library. The alias, we call it PLT for the matplotlib pyplot library. Its alias is PLT. So PLT.plot. Plot is just a function in there. And then you're going to put information into it. So Elon wrote it kind of weird in this first line. I wouldn't do it like this, but I would do it more like the second line. So usually you put your X or your independent variable and then your dependent variable the second. So X array first and then Y array second. X array is literally just like the X, like it could be your lin space, it could be your X data, and then Y array data doesn't matter. And here's an example of it. So let's say we make X is equal to np.a range 3, and then Y is equal to 2x. So that's, you know, just a nice slope. Y equals mx plus b plot. You plot them and you should get this. Although I would recommend you do lin space to like make sure it's like evenly spaced out. Since it's a line, it just connects the dots and there's no variation, so it doesn't really matter. But we'll show more examples of higher resolution. Yeah, and then at the end of your plot statement, you should always include this thing. I can't show it with my mouse because of the little bar, but it says plot.show at the very, very bottom. This tells the library in Jupyter Notebook, hey, I don't want to do anything left with this picture. It's done. That's the end of that picture. Move on to another thing. So I always recommend putting a plot.show at the end of anything you're plotting. And technically, you're supposed to put a plot.figure at the top, but it's not the biggest deal in the world. And we'll talk more about when it's necessary and when it's not necessary later. So let's say you want to do a curve. How about we do np.a range 3, right? We do our, like, this is just giving us a list of numbers 0, 1, 2, and then we do y is equal to x squared. Well, you're going to get, if you do the same idea, plot.plot x, y, now you have a point here at 0, 0, you have a plot point here at 1, 1, and then you have a point here at 2, 4. And it's discontinuous, right? So if you want to make it smooth, you need to use a lin space, as seen here. So let's put 100 data points in between there. And then now we'll connect the dots by a line. And it should look something a lot smoother like that. So just for clarity, this is 3 data points that it's connecting the dots for. Definitely not a smooth trend, especially if you're doing a like x squared plot. But if you're doing a continuous plot, you're definitely going to want to add more data points. So we put 100 in there, and it makes it nice and smooth. Cool. Now, if we do like x equals np dot linspace from 0 to 2 pi, we put 100 data points in there, evenly spaced. Now let's plot sine and cosine. And actually, we'll put them on the same curve, or I mean on the same figure. So the way to put multiple things on the same figure, before you do a plot.show statement, you just put as many plot.plot statements as you need. So what this will do is it'll literally put np.sine and np.cosine on the same graph. I believe cosine is the blue one and sine is the orange one, and we'll put them on the same plot. And you could put another sine curve. You could put however many functions you want on here. You could put x squared. It doesn't matter. But just know that as soon as you put that plot.show, it cuts that figure off and you're done. That's that. There's nothing going to be added on top of that figure anymore. If you do another plot.plot statement after the plot.show, it'll make a whole nother figure, whole nother image to look at. Yeah, so let's say I want 4 curves now. So we do x equals np.linspace. It's very standard practice. You're always going to use a linspace, or I can't say always, but almost always. And then like if we want to do 4 different curves, we can actually do like a for loop, right? Where we're varying the exponential power law by some index p. So this is a good application of a for loop. You might need to do this on a homework assignment. Say you want to iterate over like different power laws or different yada, yada, yada parameters. You can do something like this. So 1, 2, 3, 4 is our list that we're iterating over. You do this, and then, hey, this is a x to the 0, or x to the 1, x to the 2, x to the 3, x to the 4, and so on. Cool. Plotting points, scatter plots. So you can do more than just a continuous function that is like drawn by a line or connected the dots by lines. You can actually plot like the individual dots, because some data you obviously don't want to connect the dots. It would be weird, especially if it's like random data. So if you want to just generate your own random data, use that that NumPy random library, or like the random feature of the NumPy library, or you could just use the random library. Doesn't matter, however you want to do it. And then you could do plot.scatter instead. So before we were doing plot.plot, now we're using plot.scatter. This is just another like plot function in the library. And there's lots of different things you can do, but plot.scatter is very common. So if we plot our x and y data, it's just random. It will just give you a bunch of little dots on your plot. Okay, and then you end it by a plot.show. So there's different types of plot in one. So this is a lot Elon wrote, but just say xx is equal to linspace from 0 to 2 pi. Yy is the sine of 0 to 2 pi with that linspace. And then x is we do like a different x and y where it goes from 0 to 2 pi, only 20 data points this time. And then we're doing sine shifted up by 0.5. And then what this plot is doing is he's going to do a scatter plot instead or we're going to do a scatter plot for the sine curve, the second sine curve shifted up by 0.5. And what that does is it looks like this. So we're actually plotting like the 20 different data points as their own dots, not connecting by a line. Whereas in the first XX, YY, what we were doing was making it continuous by a smooth curve, by using the like 100 data points and using dot plot instead. Yeah, is there any questions so far? Okay, cool. Feel free to just interrupt me if I don't explain anything well. So astronomers have the best plots, hands down. We always make the best plots. I'll take that to the grave. Plot.scatter. So there's lots of different arguments. Same thing with plot.plot that you can use, and this will be heavily explored in one of your homework assignments. And you will have to or you won't, yeah, you'll have to use it in your homework assignments, but also we made a plotting guide, I call it the ultimate guide. And if you walk through it, it should help you with any plotting assignment you'll ever have to deal with. It's got like everything. It walks you through how to make more and more complicated plots, how to make really, really complicated plots, how to make different figures on the same picture, how to put like subplots on there and how to do 3-dimensional plots, how to plot like lots of good stuff, and all the different things you can do with it. There's lots of variations you can do to make your plots super pretty. So for example, if you want to change the color, you can say color equal to red. You can put the C for short, doesn't matter. You can specify the string. Matplotlib has like, I think 500 plus different colors to choose from, or 200 plus colors to choose from. So if you want like a specific shade of green, you can do that to make your plot look really pretty. You can change the size of the data points, the thickness of the lines. You can always do that. You can change the opacity going from 0 to 1. So 0 being super transparent and 1 being full opacity. And then you can do like change the marker style. So if you want, you could do like stars, you could do triangles, you could do squares, you could do circles, you could do filled circles, open circles, it doesn't matter. There's tons of different options out there. You can add labels to your plots like X label, Y label, so on. And there's a bit more advanced stuff that we'll start covering on Wednesday. But also for those of you that might be colorblind, or if you know people that are colorblind, we generally try to make sure that our plots are colorblind friendly. And then taking you to this link here, you can explore a little bit more colorblind friendly plots. Typically, you want to avoid using red and green because that's the most common form of color blindness. But yeah, so we always try to be conscious about that. And I believe, yeah, that's everything on the lecture for today. And I was going to do a little bit of a demo with how to do plotting. And I wanted to show you guys the Matplotlib guide before you head out. So is there any questions about lecture? Cool. So if that's the case, let's do a little bit. Let's do a little bit of demo then. Do a new window, and we will open up a new Jupyter notebook. Give me one sec. So let's go ahead and show you. What we're going to do first is look at the guide, the plotting guide, and show you guys exactly what you need to see. There we go. So I'm going to upload this to the files on B courses, so you'll be able to download it for yourself. But it's going to look like this when you open it. As soon as it loads. Yeah, and so this will walk you through, like, this should be, you should look at this when you're doing your homework, anytime you need to plot, until you feel really comfortable with plotting. You should take this. I want you to download it, study it, keep it for reference when you go do your own research with maybe a different person or PI or whatever in other classes. This should help greatly. I put this together based off of my experience with Physics 77, doing research in several different research groups after teaching this. Oh, zoom in, thank you. And so on. And I'll just walk you through basically the structure of it. We start off with the very most basics. We call it the preamble. This is where you import all your statements. Don't worry about the SciPy to optimize. We will cover that much later, probably next week or something like that. But it walks you through how to make a basic plot, then how to make your plot a little bit more complicated, say by adding a title, X label, Y label, and you'll get you will get very used to all of these different arguments or all these different like methods or functions or whatever. You almost always use a plot.figure. You almost always use a plot.title, X label, Y label, and then you plot whatever data. This plot.plot could be a figure, or I mean, it could be a scatter, it could be a histogram, and so on. And I always end with a plot.show, and this is kind of like a complete plot statement. And you'll see this is what it translates to. You get like your title, Y label, X label. You can change the size of those. You can change the fonts. You can change a whole bunch of stuff. And I walk through that a lot. in this guide. So here's plotting like a sine curve. We talked about that earlier. You could plot multiple things on top of each other, sines and cosines and so on. You can make your figures bigger by changing an argument like fig size. Don't worry about memorizing all this. I encourage you just look to keep this guide with you, like in a tab, and just like kind of always reference it when you're doing your homework assignments, to make really pretty plots. How to save a picture of a plot. We'll talk about that a little bit more Wednesday, I believe, and so on. There's lots of stuff in here. How to do error bars, log scales, histograms. There's subplots. We'll talk about this on Wednesday because those are a bit more complicated and so on. And it gets much more complicated. There's examples and all sorts of fun stuff that you can learn. Don't worry about all this. You'll see, you can open it up and explore it for yourself. You could plot pictures. You could do fancy data points. You could do polar coordinates. You could do contour plots. You could do all sorts of good stuff. So this will be available. I'll upload this today. I don't think you need it for this homework, but I'll make sure that it's available starting today in case you want to look at it. So that is the ultimate plotting guide. Would you guys like me to go over like an example of doing a plot, or do you feel like you kind of, with this, you feel like you can do it?
I think an example would be good.
Okay.
If you have time, could you go over like how to put like data from a file into a plot?
Yes.
Okay.
Yes, we can do that. Thank you for asking. So how about let's just make a new notebook right here. Okay. So almost always import numpy as np. Yeah, and import matplotlib dot pyplot as plot. And I like to do something called, where is it? This is not required, but I think it makes it look, or it makes sure that if you're like working on different systems and whatnot, it just keeps it in line. So it's called matplotlib inline. Don't worry about it, it's not important. There's like one that's called notebook. There's different things that make it more interactive. That's more advanced stuff. If you have questions about that, come to office hours, but don't worry about it. So let's make our X list or our X array. We always do np.linspace. And we've done a lot of sine and cosine stuff. Why don't we let's do between -10 and -10 and 10. And we'll put 100 data points in there. I think that's fine. We could say y is equal to, zoom in, there we go. So Rob, is that good? Can everybody read that? All right, cool. So actually let's yeah, that's fine. We could just do a function. I don't know, we'll do x cubed. How about that? We'll do x cubed for fun. And notice the beauty of like an np array or numpy array. Linspace is an array from numpy, is that you can just do simple simple stuff to it, or not stuff, but you can do simple operations to the whole array, and it's no problem. If you tried to do this with a list, it would throw a fit, right? It doesn't know what raising a list to the third power means. But NumPy knows exactly what you mean. It means you want to take every item or every number in that array and you want to cube it. So that is one of the beauties of NumPy. It's why a lot of people in the science community use it, because if you just want to do like something like x cubed, or let's say you define a function that maybe it's like the black body spectrum and it's some really gross Planck function that has exponentials on the bottom with like plus or minus like different factors, and you don't want to deal with that. Doing that with a list is kind of painful. So doing it with an array is a lot easier. It knows what you're talking about. It knows what you want to do, and so on. So anyway, we have our x and y. I always do plot.figure to start, right? And then we do plot.plot if we want to make it continuous, like where we connect the dots, or we do scatter if we want to make it discrete. So I'm going to do plot.plot because I want to make it continuous. I have 100 data points here. And I'll just plot X and Y to start off with. And then always remember to plot.show at the end. It's not required, but if you don't do it, I'll show you what happens if you don't do it. So this is what it looks like when you do just those 3 basic arguments. That's like the most basic plot you can make. And if you got rid of plot.show, just so you know, it just kind of like leaves this line here. It's like kind of ugly and it doesn't cut off the figure. So if I wanted to, do some blah, 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 right? I'm doing my code and then I go to do plot of, 2 times X and 1/2 times Y. And we'll just comment these out. Just so it doesn't give me errors, but like you're just coding a lot farther down, it'll just add it to that figure. Whereas if I did plot.show, what this will do now is it makes one figure of the original line that I wanted, and then it cuts it off, and then we do another figure for the different curve. So that's like one of the main reasons why I always advocate do a plot.show, and I always recommend doing a plot.figure at the top to indicate that's where you're starting a figure. Now, how do we make this more pretty, right? Because that's a pretty ugly plot. I would never show this to anybody. So let's do a couple things. First, we can make it bigger. So to make it bigger, there's an argument in here. It's in the guide, but don't worry about it. It's called fig size, and you set that equal to a tuple, where the x, or like the first index or the 0th index, is your x width in some units. I don't know what they are. I usually just go straight to 12/8. That's like x and y is x is 12, 8 is y. It's like an aspect ratio or whatever. And what that'll do is makes it much bigger, a lot less painful on the eye, a lot easier to see. And then it wouldn't be an actual plot without a plot.title. So we could do stupid cubic is the name of my title, and it'll add stupid cubic. You can do plot.xlabel and so on, and this is like x-axis, and you can just keep adding stuff like that. There's lots of stuff you can do. You can change the color. So let's just say that I want color equal to, we'll call it red. You can change the color to red. In fact, if you wanted to, you could, I don't know. Alpha is the argument we use for opacity, so you can change this to 0.5, and it would make it kind of like a lighter shade of red, or like a more transparent shade of red, so on. There's lots of really cool stuff you can add on to that. And by similar logic, you could do the same thing with a scatter plot instead of a regular plot, and you'd see the dots kind of like that, and you can change what the markers are. So let's say instead of dots, we wanted, I don't know, stars. You can, it's kind of hard to see, but you can do little stars, you can do triangles, and so on. If you wanted like tiny little dots, you can do like pixels with periods. Those are kind of fun. Anyway, so that's kind of like a basic example of plotting. And then somebody said, or you said you wanted to see file IO, right, with numpy.load text. So let's go ahead. I don't want to go in there because that would give you answers. Yeah. I don't have like a data file on hand. Maybe like, I just want the file. Okay. How about, I don't want to like accidentally give you stuff here. Give me 1 second. I will re-navigate. I'm going to, yeah, here's what I'll do. Yeah, okay. I need to, I guess this might work. No. Yeah, okay. I got to stop sharing my screen. And then I will, give me 1 minute as I re-navigate. So we will go ahead and open a new notebook. I believe I have some examples from Physics 77 that we can use. It was, I think it's spring 2019. Yeah. It would be like my file, it would be like homework, it would be like, oh crap, I don't remember. All right, I'm gonna stop recording the lecture because it is 6, and then I'll just leave it on, or I'll leave the call on for those of you that want to stay. That way I'm not wasting people's